All right. So this will be an introduction presentation for the upcoming series of talks on energy science. My name is Eric Hammer, and today I will explain some of the high-level perspectives that I discovered during my thesis research, namely paradigms, anomalies, and the structure of scientific revolutions. Now, my thesis topic was looking into various novel technology innovations in the energy sector to try and better understand how novel energy technologies could compare to existing solutions at a conceptual level. So, in the thesis, I used qualitative and quantitative tools to estimate the potential. Now, this presentation is not exactly on the thesis topic, but rather on these paradigm perspectives I discovered. So that will be the main focus going forward. Just a short background about myself. I received a bachelor's in electrical engineering from the University of Victoria in Canada. Then recently I finished a master's in management science under the chair of technology and innovation management at TU Munich. And then I previously worked in California at Tesla, in which I specialized in sensor development and integration for ultrasonic and radar systems. And then this year I started a new position at Quantum Power Munich. And I met the QPM team through an MIT hosted conference by the Unlab. This was in 2022, and it was a conference on new energy systems and repulsion. So that's how I made contact with Marcus and Eckhart and Christian. And now I am joined the team in January. So I'll start with an overview of the talk today. First, I'll provide a background of how I stumbled into this topic with looking at questions of innovation and technological change. Then I'll explain the details of the theory of paradigmatic cycles with historic as well as present examples. And this section covers these topics, which will be the majority of the topic of the talk today. And then in the end, I'll explore applying this theory of paradigmatic cycles to energy science and compare and contrast economic and social perspectives. And lastly, I'll look at potential solutions to improve the overall rate and diversity of scientific discovery. So in developing my thesis, I wanted to explore the factors that drive major innovation and technological change, such that I could later apply these findings to the energy technology sector. So here we have, for example, the Wright brothers with their first flight. Next to that is Sigmund Freud, the founder of psychoanalytics. He had ideas that changed medical science and started new branches of research. Then here, the Saturn V rocket, representing the use of Newtonian equations, which were first used for rocketry between 1890s and the 1920s. Then in the 1920s, we had the burst of research in quantum field theory. So we have all these founders of quantum field theory. The bottom left shows a photovoltaic cell. The photoelectric effect, this was actually discovered in 1839, but scientists didn't understand how it worked until much later. Next to that is a depiction of the heliocentric model that outdated the idea that the sun revolved around the Earth. And lastly, we have Charles Darwin's theory of evolution, which replaced traditional views of creationism and fixed species. Now, these are just some of many famous examples, but this is where I started my thinking process. I was asking myself, what did all these discoveries have in common? Is there an overarching theory that describes and encompasses the mechanisms behind these sorts of scientific changes and breakthroughs? This is where I discovered the work of Thomas Kuhn. He was an American philosopher of science whose work on the structure of scientific revolutions brought a new perspective and on the way that scholars understand the history of science. He earned his PhD in 1949 on the concept of energy in early modern physics, and his seminal work in 1962 ended up popularizing the term paradigm shift. His ideas don't only provide this high-level structure of the scientific perspective or scientific progress, but I think it also creates an exciting framework how to inspire and stimulate scientific discovery. So to begin, when we think of any scientific theory, there are observations and a hypothesis or a model. This is what Kuhn was doing with historical analysis as the foundation for his theory, with time in history on the x-axis, and scientific achievement could be viewed on the y-axis, although in practice, the details of x and y positions are more abstract and complex. He encompasses the importance of historical data nicely in this opening statement. History, if viewed as a collection of more than just a sequence of events, could produce a decisive transformation in the image of science. I think his reasoning for using history's data points are sound. Like any scientific data, researchers search for patterns, and the patterns Kuhn discovered are quite compelling. He also argues that studying the history of science is essential to understanding how scientific knowledge is gained, accepted, and assimilated. To overview the paradigmatic cycle, it can be stated as a process described by Kuhn in which science progresses through periods of normal science and extraordinary science. During the normal phase, anomalies are found and are either solved within the existing worldview or paradigm, or they lead to extraordinary science. If extraordinary science is successful in resolving the anomalies, then this can lead to a new paradigm and possibly a scientific revolution. During a revolution or paradigm shift, the old paradigm is replaced with a new one, and this process is cyclical, with each paradigm shift leading to a new period of normal science. We can kind of see this play out in a high-level picture iteratively within the cognitive revolution during the mid-20th century. This is where Sigmund Freud's psychoanalytical theory first replaced existing views on the nature of mental illness and human behavior. And after this first paradigm shift in psychology, others followed, such as behaviorism and humanistic psychology. These challenged Freud's ideas and resulted in more redefined paradigms. So to understand this cycle better, I think it makes sense to dive into the structural elements Kuhn defines, starting with paradigms. According to Kuhn, paradigms manifest at the start of a universally recognized scientific achievement and share two fundamental characteristics. One, it attracts a group of followers away from competing modes of scientific activity. And two, the paradigm is open-ended to leave all sorts of puzzles for the redefined group of scientists to resolve. In Kuhn's book, there are many uses of the term paradigm, and it's actually one of the more difficult concepts to grasp, but in general, the idea of paradigm can be broken down into global and local paradigms. I've illustrated these groupings here, where the global paradigm influences all the sciences, whereas the local paradigm is mostly influencing the related sciences. Here we can understand in detail what is meant by a global paradigm, or what Kuhn referred to as a disciplinary matrix. A global paradigm consists of shared assumptions, methods, theories, and laws which help define a scientific community's worldview. Some examples listed here could be like the structure of DNA within biology, or force equals mass times acceleration, and or Maxwell's equations of electromagnetic physics. These would be considered symbolic generalizations of the global paradigm. For measurement techniques, we can think of standard electronic equipment that are used across all sciences. And in life sciences, you can think of surveys or standardized tests that everyone is familiar with. With models, we have commonly used models that are understood across many sciences, such as the Bohr model of atom or tectonic plate movements in geology. Methods like carbon dating and machine learning are popular in many sciences. And lastly, in a global paradigm, you have shared commitments like natural selection in biology and fundamental particles, or the conservation of energy in physics. From these examples, we can see how these characteristics of a global paradigm apply to a wide scientific community, such as in the areas of STEM, science, technology, engineering, and math. And these kind of shared characteristics they're all taken for granted. Although, as we'll come to see later, it is sometimes a good idea to question these shared beliefs. If we now look at a local paradigm, this idea was explored in more detail by Thomas Kuhn, as there are simply more concrete links to historical examples. Kuhn describes local paradigms as containing a set of exemplars that serve as models for scientists to develop their research. They include experiments, theories, and methodologies that are considered successful. And these exemplars are widely accepted by the paradigm adhering group. You can think of exemplars as the textbook problems a student would have to solve in one of their science classes. These problem solutions act as sort of a proof for the local paradigm, and in turn help align the shared beliefs of the global paradigm as well. Local paradigms also guide scientific inquiry within a specific field or subfield by shaping what problems are considered important, the design of experiments, and the influence upon how data is collected, analyzed, and even interpreted. You can also think of a paradigm as having a specialized vocabulary. When you look at different sciences, different fields, they have very specific language that's used to describe phenomena and concepts. Regarding examples of paradigm, something interesting I noticed when I was looking for proper examples of local paradigms was this aspect of the passage of time. For example, looking at Newtonian mechanics in the 17th century, it would have been considered a local paradigm then, whereas today it can be categorized as a more global paradigm. It sort of seems like the successful pieces of old paradigms shape the global paradigms of the present. And this makes sense, I think. Another example could be germ theory of disease in the 19th century, becoming a global paradigm over time. In Kuhn's follow-up writing, he was kind of self-critical of the original use of the word paradigm, as it took on a more global meaning than he would have liked. That's why he emphasized the term disciplinary matrix, because a global paradigm focuses more on a scientific community's shared values and beliefs rather than on individual scientific achievements. That's more the realm of the local paradigm. So to summarize, paradigms, global and local, shape the scientific beliefs of the individual scientist and the adhering community. They provide a sense of direction and purpose, and they help focus a scientist's efforts and increase their chances of making significant discoveries. To explore local paradigms further, Thomas Kuhn wanted to describe the day-to-day scientific activity that actually happens within them. The activity of normal science means research firmly based upon one or more past scientific achievements. These achievements supply the foundation for its further practice, Kuhn writes. In this view, normal science is cumulative and generates a stockpile of knowledge over time. Kuhn metaphorically contrasts normal science to a puzzle-solving activity. And with this metaphor, he lays out a set of principles observed, namely, a network of strong scientific consensuses encompassing theories, methodologies, instrumentation, assumptions, and facts. All of these normal science characteristics exist within a single paradigm and become the basis for scientists and researchers to study their field. I think this puzzle metaphor is an important point in order to understand Kuhn's view of day-to-day scientific activities. When we view normal science as a series of puzzle-solving games, we can clearly see that there are rules that must be followed. For example, all of the pieces must be used. Their plane sides must be turned down. They must be interlocked without forcing, until no holes remain. These rules limit both the nature of acceptable solutions and the steps by which they are to be obtained. Thomas Kuhn goes on to say, normal science problems display something much like this set of puzzle characteristics. In this metaphor, he explains that the term rule can actually mean established viewpoint in the context of a local paradigm. Therefore, we know now that the scientist is already guided by an overarching paradigm, and the established viewpoints or rules within that paradigm can explain how the scientist is guided. To break down the rules of normal science, we can understand them as conceptual rules. The rules can be these classification concepts in biology, or these concepts that particles, waves, and force fields exist in the area of physics. Conceptual rules can help a scientist organize and make sense of complex phenomena by defining key categories and relationships. You can think of established viewpoints as theoretical rules. And these can include principles of electron orbitals or thermodynamics, and they come from their respective theories. We have instrumental rules, such as programming languages and the syntax used within those languages. And lastly, we can think of methodological rules, such as in psychology or medicine, where they use control and placebo groups, and these can be also considered rules. These rules tell the scientist of some mature speciality what both the world and his science are like. Now we have another question here. What if the puzzling rules of normal science are not clear? In some paradigms, it's not always easy to discover what the rules of normal science are, and Thomas Kuhn was well aware of this fact. He says that when rules are not clear, the rules end up deriving from other paradigms. But paradigms can also guide research even without a strict set of shared rules. We can look at this picture here of a very wide road without any lane markings. And this picture kind of gives us a sense of what a paradigm without rules looks like. To illustrate how this works, if we imagine this wide road, as a single paradigm like quantum mechanics, and we have different groups studying this field, such as chemists, solid-state physicists, or astrophysicists, for example, scientists within these communities will have different understandings of quantum mechanics based on their education and exposure to different paradigms. And they will develop their own rules how to travel down this wide road. Some might be driving in the middle, some driving on the right. Some might think they're on the left lane of the Autobahn in Germany, or a British driver might be driving the wrong way. Basically, these groups will approach problems and puzzles based on their past experience, but still confined to the established paradigms. This can lead to confusion and may actually slow down paradigm progression. So I just overviewed how normal science is like puzzle solving and what happens when rules are not very clear. Now I want to explore the reasons why it is this way. To build some intuition, we can simply observe the steady flow of scientific papers as examples of normal science. We can look at advances in certain materials, or research developing smaller and smaller gate transistors. We have normal science that does a lot of validation of theoretical constants, or we have the observations of predicted phenomena expected by normal research. And you can think of incremental steps towards expanding the application of existing quantum theories as ideas around normal science. Thomas Kuhn summarizes an interesting commonality among these examples with this statement. Perhaps the most striking feature of the normal research problems we have just encountered is how little they aim to produce major novelties, conceptual or phenomenal. For the puzzling games of normal science, the solutions are typically known in advance. There are no surprises when the results match the theories. And adding one more piece to the puzzle expands the existing paradigm, expands the scope and precision. To explore these reasons in a bit more detail, we need to look at aspects of the scientists themselves, what they focus on when designing experiments. Thomas Kuhn describes that because of the adhered paradigm, usually only the most specialized details are not known in advance. This essentially creates a narrow range of expected results. We can see this how it played out in electrostatic experiments in the 18th century, where electrostatic results were mostly ignored because they did not show consistent or simple values that fit within the paradigm of electrical research at the time. They just remained mere facts and were viewed as unimportant, at least until Coulomb and his colleagues predicted the results in a later paradigm. So this narrow range of expectations is a bit problematic, as Kuhn writes. The project whose outcome does not fall in that narrow range is usually just a research failure, one which reflects not on nature, but on the scientist. Avoiding failure then becomes a strong motivator for the scientist to develop their puzzle-solving skills. Another motivator I mentioned earlier is the overall improving scope and precision of the paradigm. We also have the challenge of the puzzle itself. It serves an important part of what drives scientists to solve normal research problems. We can also look at general psychological factors that force normal science into these puzzling-like activities. Publication bias is a big one, as it creates an environment where only positive or significant results are published, while negative or inconclusive results are not shown. This means that research that challenges the paradigm or fails to find significant results may be less likely to be published or accepted by a journal or scientific community. There are other things like general peer pressure, the more primitive social behaviors, and reputation that is maintained by staying an expert puzzle solver. I think these aspects add another depth to the puzzle metaphor, which can be helpful to understand the normal science process, as this process tends to happen over very long periods of scientific development. So the key takeaways here are on normal science. Paradigms still guide normal science even when no explicit rules exist. We saw that with the wide road analogy. Normal science does not aim to produce major novelties. We see this through the established viewpoints or rules that are followed, where problems are assumed to have solutions driven by the paradigm. Also, only certain problems are considered important. This means scientific communities only allow problems that can be solved within the paradigm and may reject other problems as metaphysical, irrelevant, or too problematic. This rejection can be seen when we look into the topic of thermodynamics, for example. At the Unlab MIT conference in 2022, Professor Daniel Sheehan from the University of San Diego Department of Physics stated multiple exceptions highlighting the nuanced definitions of boundaries in thermodynamic systems. He said, to put this into perspective, the second law has been undergoing really unprecedented scrutiny over the last 25 years. Roughly 46 second law challenges have reached into the scientific literature since the mid-1990s. So we see that still these thermodynamic problems are mostly ignored. Lack of major novelty discovery is also a consequence of the fact that normal research remains focused and undistracted. We see how normal science can insulate scientists from socially important problems that cannot be reduced to the puzzle form and are not stated in terms of the paradigm's tools, as these problems can be a distraction. Some examples could be cold fusion, zero-point energy, or anti-gravity research. Thomas Kuhn summarizes this here. A scientific community chooses problems that are assumed to have solutions. These are the only problems that the community will admit as scientific or encourage its members to undertake. The characteristics of normal science we saw also motivate scientists to become expert puzzle solvers to extend the scope and precision of the paradigm. Now, although it looks like Kuhn defined normal science in a bit of a negative light, he was more focused on what the actual truth is for scientific evolution. And part of that truth is that there are these periods of normal science activity, which is not a bad thing. Kuhn made a nice quote from Francis Bacon. Truth emerges more readily from error than from confusion. This quote can be used to contrast pre-paradigm research patterns where there's simply no wide road for scientists to travel on and there is just confusion. In normal science, however, scientists can focus on discovering the esoteric details of their experiments. By finding the small errors in their assumptions, they are simply accumulating scientific truth and thus evolving science, but just in a slower way. A little interesting note is that we'll see how the portion of this quote, truth emerges more readily from error, relates to the discovery of an anomaly in the next slides. Now, within a Kuhnian paradigm, normal science plays out as these various puzzling games. So we have these different groups of scientists working on their different puzzles, finding new pieces and expanding the paradigm. But then they encounter this. What happens when a piece of the puzzle doesn't fit? Thomas Kuhn refers to these as anomalies and defines them with a number of characteristics. In technical terms, an anomaly is a scientific result or observation that violates the expectations set by a paradigm. They are typically discovered in these types of ways: by errors or mistakes, such as the traditional view that orbits were circular until the discovery of elliptical orbits by Kepler. Anomalies might occur through new experimental equipment, such as cloud chambers for observing cosmic radiation, or by scanning tunneling microscopes, where in the 80s they found these microstructures called quantum corals. They're like rings of atoms. And these were not explainable at the time by solid state physics. There have also been famous examples of accidents leading to the discovery of anomalies, like X-rays, where they saw that a leak from a cathode ray tube experiment was causing this X-ray sensitive equipment in their lab to glow. Thomas Kuhn writes, "Though X-rays were not prohibited by established theory, they violated deeply entrenched expectations. Those expectations, I suggest, were implicit in the design and interpretation of established laboratory procedures." There are also examples of researchers studying outside the paradigm leading to anomalies. Like in the 18th century, Alexandre Lavoisier set up a combustion experiment that showed how oxygen was needed for burning, not the release of this imaginary substance called phlogiston. We also have theory-induced, and these are theory-created anomalies, which sort of sound a bit contradictory, but take the Leyden jar discovery story. This discovery took place in the mid-1700s, where scientists were guided by the prevailing theory that electricity was a fluid, and they were attempting to store this electric fluid inside a water-filled jar. To their surprise, when they touched the outside of the jar, they received an electric shock, resulting in the recognition that electricity was not a fluid, but rather a form of electric charge. Now, you could argue this example was a discovery by accident as well. So in general, it would be accurate to say that an anomaly can be discovered by more than one of these discovery features. So you could have new experimental equipment and accidentally discover an anomaly, or you could have a researcher studying outside the field making an error or mistake in their measurement. And so, yeah, you can have multiple methods in which an anomaly is discovered. Switching to a more present example of how anomalies can be discovered, we can have a look into quantum mechanics at this process of renormalization. Renormalization basically gets rid of infinities when applying equations of quantum theories to different applications. It involves an arbitrary choice of the cutoff parameter used to regulate divergences in perturbation calculations. And the problem with doing this is when the theory's predictions change, when the choice of cutoff changes and doesn't align with experimental results. This, by definition, makes a theory incomplete or inconsistent. Some examples of or issues due to renormalization are like the mass of the Higgs boson, as this depends on the renormalization scheme used. You can also look at the G factor, or the anomalous magnetic moment of the electron, as there's a small discrepancy between experimental result and theoretical prediction, which is also attributed to this renormalization scheme. The cosmological constant is considered one of the biggest problems in science, because the renormalization value is orders of magnitude different than the observed value. Also, examples of the Lamb shift depends on the renormalization scheme, as well as the Casimir effect. So how does this renormalization example relate to the discovery of an anomaly? Well, in quantum theories, it is implied that these infinities exist. They are in the equations. However, the renormalization process is being used to remove the infinities in order to match the theory's predictions to experimental results. So if we were to position ourselves in the future where we have a new quantum field theory that is self-consistent and predicts experimental results without renormalization, then we can say that the infinities anomaly was theory-induced, similar to this Leyden jar discovery. It's basically the story of scientists building more and more precise experiments to try and align the theory with observations, and then anomalies start appearing. Another interesting aspect of anomalies is the idea of a perception process. Thomas Kuhn uses a psychological experiment by Brunner and Postman to show the perception of an anomaly does not necessarily make it self-revealing. In the experiment, subjects were asked to identify a series of playing cards. While most cards were from a normal playing deck, the experimenters inserted a few anomalous cards like a black 4 of hearts or a red 6 of spades. The participants were shown the cards at first for a very short amount of time, and then after increasing the exposure a bit more, and this is on the order of tens of milliseconds, all participants identified the cards as normal, without hesitation or puzzlement, meaning they did not recognize the anomaly. Instead, they fit the card into a conceptual category based on prior experience. Then, in later rounds, longer amounts of exposure time resulted in most participants beginning to show signs of hesitation and confusion until they began to correctly identify the anomalies. This realization allowed them to recognize the other remaining anomalies more easily. But some subjects were never able to recognize all the cards, even after 40 times the average exposure. At least 10% of the cards, of the anomalous cards, remained unidentified. These participants often experienced acute personal distress. One of them exclaimed, "I can't make this suit out. Whatever it is, it didn't even look like a card that time. I don't know what color it is now or whether it's a spade or a heart. I'm not even sure now what a spade looks like. My God." Here, we can see that upon recognition of anomalies, a sort of crisis can begin. Now, not all anomalies lead to crisis, but when a significant number accumulate, a crisis can occur. This leads to insecurity within the paradigm, as these anomalies undermine or call into question the reliability of the established framework. Thomas Kuhn writes, "Insecurity is generated by the persistent failure of the puzzles of normal science to come out as they should." Basically, the paradigm is no longer able to provide satisfactory answers to the community's scientific questions. New technologies or methods may even reveal previously undetected phenomena that the paradigm is unable to deal with. Crisis can also come from an external societal aspect. Demand for new solutions to global problems, energy independence, for example, and looking into new frameworks to help address these problems. And from the past, you can think of miasma theory of disease, which was like when they thought dirty air or vapor or smells kind of caused the spread of disease. Well, this would fit with this category of crisis, as there was a societal need to understand and address the spread of infectious disease. Germ theory eventually replaced the miasma theory. From the history of science, we can see a few more examples of crisis. Ptolemaic astronomy produced a number of anomalies, such as inaccuracies in predicting location of celestial bodies and motion of planets, leading to the replacement by Copernican's heliocentric model. In physics, Kuhn shows how crisis in Newtonian mechanics was driven by anomalies in the orbital precession of Mercury and also a failed understanding of wave mechanics through the Michelson-Morley experiment. Einstein's relativity theories brought solutions describing gravity as curved spacetime. There was also a crisis in chemistry in the 18th century on the topic of air. As I mentioned earlier, phlogiston theory described how materials lost weight when they were burned through the release of this imaginary substance called phlogiston. Many anomalies in phlogiston theory led scientists to try and make new theories and experiments to reconcile these issues. An important point here is that by the time Alexander Lavoisier began his experiments on airs in the early 1770s, there were almost as many versions of the phlogiston theory as there were pneumatic chemists. We can start to see something similar happening in today's modern quantum mechanics. There are all these competing quantum field theories. It makes me wonder, are we in a crisis? Thomas Kuhn says that the proliferation of versions of a theory is a very usual symptom of crisis. Something to think about here. So we had crisis, and within a scientific crisis, we start to see something like a new pattern, a new research pattern beginning to form. And Thomas Kuhn described this as extraordinary science. He captures it nicely in this quote: "When an anomaly comes to seem more than just another puzzle of normal science, the transition to crisis and to extraordinary science has begun." He goes on to say that the anomalies themselves come to be more and more generally recognized as such by the profession, and more attention is given to them by an increasing number of the field's most well-known scientists. This focus on anomalies is characteristic of extraordinary science and forces scientists to rethink the rules of normal research, similar to what Kuhn is saying here about loosening the rules of normal science. Part of this focus involves identification and documentation. So we have systematic investigation of observations to more precisely know the anomaly's structure and to understand the extent to which it contradicts the prevailing paradigm. There's also prioritization of anomalies that involve redirecting resources for documentation efforts, as well as cross-validation and replication. This ensures robustness of anomalous findings through independent verification. Another aspect is the reevaluation of core assumptions. A critical examination often occurs that involves the debate and scrutiny of fundamental principles of the existing paradigm. This can further lead to expressions of explicit discontent via the publication of papers highlighting anomalies and criticisms of the existing paradigm. Exploration of alternative explanations by considering alternative theories that might account for anomalies more effectively. Scientists practicing extraordinary research often fall back to philosophical ideas as well. They begin the study of knowledge, nature, and reality, and this helps them better understand core assumptions and concepts. These investigations can further inform new frameworks to produce alternative theories. So the fallback to philosophy is often a strong characteristic of extraordinary research. Now, what is an extraordinary scientist, you might ask? Well, directly from Kuhn, he will look almost like our most prevalent image of the scientist. He will, in the first place, often seem a man searching at random, trying experiments just to see what will happen, looking for an effect whose nature he cannot quite guess. The extraordinary scientist is open to new ideas. By challenging established norms, questioning conventional wisdom and long-held beliefs. They incorporate insights from different fields to develop novel approaches. They also encourage creativity and foster an environment that promotes innovative thinking and risk-taking. As a result, we have speculative theories that start to form and an attempt to build hypotheses and experiments around. Kuhn makes an interesting note on this point in that because the scientist is not invested in the previous paradigm, they can more easily abandon their theories with relative ease if they're unsuccessful. They're basically less committed to following established rules. The scientist practicing extraordinary research does so with experimental innovation. Novel experiments that push the boundaries of current knowledge and challenge existing paradigms. These experiments are usually developed with a goal-oriented mindset and with rapid iteration so that failures can be learned from quickly. Experimental innovation might be enhanced by the adoption of new technologies, like utilizing cutting-edge tools and instruments to gather new data or enhance the analysis. In all these processes, the development of new techniques, technologies, or inventions can also be a likely outcome. And this statement here basically captures all these aspects. We have abandoning standard practice, exploring new and unique experiments, deconstruction of stereotypes, creating speculative theories. Lastly, in the paradigmatic cycle, we have revolution and incommensurability. Kuhn provides a lot of details in these sections, but since I've covered many details already, I'm just going to provide the rough outline of what he means here. The key takeaways. For the definition of revolution, we can understand it as a paradigm shift or paradigm change. The new paradigm brings about a reorganization in the way scientists perceive their field. It often presents fresh concepts, methodologies, and approaches to data interpretation that are fundamentally different from those found in the preceding paradigm. This is essentially a radical change to scientists' beliefs. Because one paradigm is replaced by another, revolutions are also non-cumulative. They do not simply add knowledge to the existing framework. And this is because the new knowledge is incompatible with the old way of thinking. For example, the caloric theory of heat was simply not compatible with kinetic theory, which demonstrated how energy is conserved through the motion of molecules. Not to say that revolutions do not have some aspects that build upon previous paradigms, but many aspects need to be abandoned or modified, making the revolution process overall non-cumulative. Since crisis was the accumulation of anomalies, revolution is thereby the resolution of them. We can say that the new paradigm solves the anomalies, evolves scientific understanding, rebuilds scientific consensus, and can have major technological impact. Resistance to change is another major aspect that underlies revolutions, as we can imagine, since we're talking about changing a scientist's belief about the nature and the world around him. Kuhn explains that younger scientists generally find it much simpler to adopt the new paradigm compared to older scientists. Eventually, some older scientists do switch sides or allegiance, but not all. And various factors contribute to this behavior, but discussing them in detail is beyond the scope of this discussion. The last point is the term incommensurability. Kuhn introduces to help define the communication that happens between scientists during a paradigm shift. It is also part of the reason why resistance to change is observed. Each group uses its own paradigm to essentially argue in that paradigm's defense. It is a little difficult to describe incommensurability in a concise way, so I'll read a paragraph from my thesis that I think captures the essence. The two phases of scientific progression, the normal and extraordinary, are not just different speeds of science, but fundamentally different approaches to scientific work. This contrast of scientific method often leads to disagreement between the two practicing groups. Consequent novel discoveries from extraordinary research may necessitate the need for a new paradigm, which further escalates criticisms from traditional practitioners. Kuhn describes this disagreement as resulting from the incommensurability of two competing paradigms. The proponents of competing paradigms practice their trades in different worlds. One contains constrained bodies that fall slowly, the other pendulums that repeat their motions again and again. In one, solutions are compounds, in the other, mixtures. One is embedded in a flat, the other in a curved matrix of space. Practicing in different worlds, the two groups of scientists see different things when they look from the same point in the same direction. They observe differences about foundational questions, such as the existence of subatomic particles, the materiality of light, and the conservation of heat or of energy. These are the critical differences between successive paradigms. The two schools even begin disagreeing on what is a problem and what is a solution, leading to cross-purpose debate on the relative values of their respective paradigms. Ignorant of their incommensurable perspectives, Kuhn cites multiple instances illustrating the outcomes of incommensurability. X-rays, however, were greeted not only with surprise, but with shock. Lord Kelvin at first pronounced them an elaborate hoax. Or the layman who scoffed at Einstein's general theory of relativity because space could not be curved. It was not that sort of thing. Consider, for another example, the men who called Copernicus mad because he proclaimed that the Earth moved. Even Darwin understood this concept of incommensurability in his writings. Although I am fully convinced of the truth of the views given in this volume, I by no means expect to convince experienced naturalists whose minds are stocked with a multitude of facts, all viewed during a long course of years from a point of view directly opposite to mine. So I hope that gives an okay understanding of incommensurability, how the old and new paradigm groups have difficulty communicating during a revolution. So in summary, the paradigmatic cycle consists of global and local paradigms that guide the research of normal science. Normal science plays out like a series of puzzling games with a set of shared rules. And when the shared rules don't exactly exist, a scientist will fall back to their default research behaviors, still guided by different paradigms. Anomalies occur when a piece of the puzzle doesn't quite fit. And an accumulation of these anomalies can lead to crisis if they cannot be solved by the existing paradigm. Extraordinary science happens within a crisis and attempts to solve the anomalies in creative ways. And finally, if the extraordinary science research or science is successful, then a paradigm shift can occur and lead to revolution. Assuming all the issues of incommensurability can be solved and enough people join the new paradigm, sort of like a political revolution, then the new paradigm replaces the old and a new phase of normal research begins. If we reflect now on normal versus extraordinary science, when we compare these two patterns of research, we can see how, first, normal science is a necessary part of the paradigmatic cycle, as it helps guide and focus scientists on their research while minimizing potential distractions. This focus is actually good for uncovering anomalies because small errors in the details of normal science experiments can accumulate. Kuhn sums this up nicely in this quote: "Resistance to paradigm change guarantees that scientists will not be lightly distracted and that the anomalies that lead to paradigm change will penetrate existing knowledge to the core. For extraordinary science, we can now see how it is actually foundational to normal science, as it helps bring closure to anomalies and provides a new way forward for the scientific field. When thinking about the characteristics of extraordinary science, Kuhn writes, "It is upon their existence, more than upon that of revolutions, that the notion of normal science depends." So I hope this gives a high-level picture of the paradigmatic cycle now. We have a rough idea of how everything is working together. Now I want to look more at a focus on the economic and social factors of energy technology development and what this looks like from a Kuhnian paradigm perspective. So to do that, I'm going to look at the social and economic factors of energy technology development and see if we can answer this question: what are the requirements for energy innovation? And if we can answer this question, then I think we can come up with good solutions by applying the parts of Kuhn's theory that predict technological breakthroughs. To address this question, I discovered the energy technology innovation system during my thesis research. We can see like this diagram on the right here kind of depicts the outline of the different steps involved in energy technology innovation. But the details of it are not so critical, more like the main points, which are in terms of the economic aspects, starting with supply and demand. We know the basics, how if demand is greater than supply, then prices rise. And new energy innovations, if we take this idea that new energy innovations need to achieve high supply and low cost. The technology development cycles describes the steps required to achieve the economies of scale required for these lower costs. And the phases are research and development, towards proof of concept, then commercialization, then scaled commercialization. But if we need economies of scale, then the focus for innovation should clearly be the first step of which is research and development. And I think that point is quite clear. The ETIS authors propose a number of ideas around investment strategies, but the main idea is that innovation in the energy sector takes a long time, so sustained and steady sources of funding are required, especially during economic downturns. Looking at more social aspects, ETIS says there needs to be sufficient knowledge and learning for innovation to grow. This involves collaboration with universities or other knowledge groups. And also having this openness to new ideas it's an essential characteristic of extraordinary science. And this also includes the interdisciplinary communication. Through demonstrations and feedback, the ETIS authors also describe various ways how this grows knowledge and learning. For the categories of actors and institutions, the need for entrepreneurs can be viewed in a similar light to extraordinary scientists we talked about earlier. The risk-seeking nature of entrepreneurs is actually needed for energy innovations to develop. Adaptive policy making, this last point here, this policy making by governments or private institutions is important because if you don't have this adaptive policy making, then long-term policies take over and can lead to something called technology lock-in. This is kind of similar to an established paradigm. Technology lock-in keeps out alternatives and enables a certain hardness to a system, and this can often represent large vested interests or incumbent actors. So to avoid technology lock-in, institutions can be encouraged to practice adaptive policymaking rather than becoming gatekeepers against new technologies. We can think of what happened with the carbon lock-in from the 70s onward to today. So going into this last section here, we're trying to come up with some solutions for the future of scientific progression. I think it makes sense to look at a reform of science education. We could start by reevaluating how we teach the history and philosophy of science. Maybe making this more goal-orientated, because it's often the case students are asking, why am I learning all this history for? Like, what use is it to me? Well, I think if we can teach it in a more goal-orientated way towards like how you can make a major discovery if you're more open to extraordinary research, for example, that might inspire students to be more interested in learning this. So yeah, teaching the historical development and the evolution of science, and exploring the key scientific discoveries, the paradigm shifts, influential scientists, and the development of scientific methods, highlighting the events and factors that shape the growth of scientific knowledge, I think is important. We can also teach philosophical and societal implications by examining the relationship between science and society, including the role of science in shaping culture, political, and economic systems. I think if we understand these perspectives better, then that can help inform policy-making decisions. Science education should also help equip students for paradigm shifts. This can be around developing critical thinking and intellectual openness, teaching students to understand the importance of anomalies, to evaluate evidence by analyzing theories systematically, enabling them to question certain established beliefs and maybe embrace different perspectives. In training for paradigm shifts, we would also want to encourage creative problem-solving skills. This can be developed by students by working across different disciplines outside their primary field, having different interdisciplinary experiences. To help students put their creative thinking into practice, it would be a good idea to teach innovation and entrepreneurship strategies. This can be things like design thinking, lean and efficient startup methodologies, minimum viable product, market research and analysis. This is like finding good market fit for the technology to grow, and even risk assessment and minimizing perceived uncertainty, which is important for the entrepreneur. All these are strategies that can be taught. On the policy side, I think there needs to be a perspective shift in understanding the importance of extraordinary research. I would propose funding ratios, for example. A more balanced approach can promote a healthy ecosystem of diverse research, fostering both steady progress and groundbreaking discoveries. Because currently, right now, we have 100% funding going to normal science. But if we can do something like 90-10, 80-20, these ratios can just bring a healthier balance to the scientific development. Certain grants for high-risk, high-reward projects could also be created. And long-term research funding offer grants with longer durations or flexible funding structures that allow researchers to pursue ambitious exploratory projects without this constant pressure of short-term deliverables. We also would want to have policies that advocate public engagement and science communication. We should support initiatives that effectively communicate the importance and potential impact of extraordinary science to the public. policymakers and stakeholders are also included in this. We want to essentially build broader support for this type of research, as we've seen how important it is for making technological breakthroughs. You can also think of new frameworks or policies around knowledge sharing. So maybe we can encourage or incentivize collaboration between different scientific fields by having specific funding or grant schemes that encourage this type of behavior, or that are strictly limited. Like if you want to get this certain grant, you have to be working with another research lab in a different country, for example. This would be like incentivizing cross-border collaboration. So these are just some ideas to like improve this scientific development, incorporating Kuhn's ideas and showing like why we need to fund extraordinary research and why it's important. But that concludes the end of the presentation. Thanks everyone for listening, and hope we all can learn something from this.